Share screen, share whole screen. That's it. And share. Perfect. Okay, looks like we're all good to go. So apologies for a few little glitches there.
What's being shared on is not the same as what's here. It's a
yes, you're sharing the presentation view on Zoom.
Oh,
You need to the presenter's view rather than the slides. It's trying to be clever.
yeah, because I've got
So you
screen
share
duplicating
again.
on.
Yeah.
Yeah, that looks better.
Well, now it's probably the wrong one again. Right now.
Yeah.
Well done.
It makes a second screen when I.
Okay, so our first speaker for the Saturday afternoon session is Michelle Brosseau. And over to you, Michelle, for blimps.
So yeah, so I'm doing blimps in ArduPilot, and yeah, so I've been so my last talk was on just the manual mode, and so I've since added the position controller and also source localization. And so yeah, this is two of the different blimps. So this one is actually this same silver balloon but painted black because Vicon doesn't like reflection. Yeah. So yeah, that's the outline of the talk, just in case. Yeah. So we've got the introduction and some kind of recap of what I did last, with kind of the hardware and initial prototype. And then I've got yeah, how I implemented loiter mode and then source localization. So this is kind of the motivation. So blimps have a much longer flight time and better collision tolerance, and so they also don't create as much air disturbance. And so the flight time is kind of clear because they don't need to expend any energy to keep themselves in the air, and the collision tolerance is because they mostly just bounce off of whatever they hit. Whereas with quads, if you don't have shields, the rotors stop and it's bye-bye. And yeah, so they also, the not getting as much air disturbance is really important in the source localization algorithm, where you don't want to be blowing away the very thing you're trying to detect. So they also have, unfortunately, a low payload capacity because of needing to use helium. And so that's why they're very suitable for surveillance type of missions, but they don't have, so they're not going to be lifting heavy weights, but they're good at carrying a camera for that kind of, or any other sensor. So there's not really many miniature platforms, especially not ones you can duplicate. And even more so if you want to do auto missions or that kind of thing. Yeah. So these are some photos of our initial prototypes. We found out that latex balloons are not a fun idea because, yeah, if you try to, they deflate really quickly, and if you try to add air to them, they explode in your face. So that one did. And they deflated so quickly that we had to be removing ballast weight every few seconds. So this is our initial gondolas, and that's some of the that's the smaller spherical balloon than this one. So it didn't give enough weight, so we had to add another one, which was messy. So we finally found these ones, and yeah, so yeah, they're hard to get a hold of, which is some of the challenges with blimps, is finding the right yeah, airfoil and things, especially if you're not in where you're making your own envelopes. So this is now our current gondola. And so we've just got a flight controller on one side, and then Wi-Fi modules, RC receivers, all of that kind of things. So now I've got a demo to kind of show how the flight controls work.
You can move it to the office. Yeah.
I've seen people do it. It's that servo not playing the ball.
Yeah, it's not being very good, but. So you can see that is how your works. It is offset the two side ones. And so you get a rotation axis, same for height.
So cute.
And so the XY axis are of course the standard one.
Why do you guys?
These are the style shells. Are you selling them?
And it's, so that kind of shows how the axes work. And it's,
If there's aliens on Jupiter, that's a good one.
So this is also kind of demonstrating one of the applications is that because they can kind of hit things like that net that it hits on the way through, you can fit them through basically a hole that's barely as big as the thing itself. And so that's really useful for doing anything indoors where you essentially don't need to worry much about like object avoidance because, you know, it'll just bounce off it. So this is so now I started implementing loiter mode, and so this is the control architecture that I ended up with. Just a very simple cascaded the controller, and this with some constraints. So it just moves the desired position along as you move the joysticks, and then that ends up going through the fin class, which I actually did in more detail on the last one, but it just converts the 4 axes. So we've only got 4 axes control. So X, Y, Z horizontal and yaw. And so the fin class converts that into the sine wave flapping servo commands. And that ends up going through ArduPilot's libraries and ends up at servers. So we also needed to add a notch filter. Because there's a lot of 3 hertz noise because that's the speed that the fins flap at, and the whole thing kind of wobbles like that. You guys saw that in the demo. This is the kind of bit performance we got out of it, which is okay, but a lot of room for improvement, I think. So you kind of sometimes you can get about 0.3 meters or 1 meter overshoot and so on, but most of the time it's fairly good. So this is the loiter mode, and so I was essentially just pushing this XY stick in the 4 directions to do a rectangle, I think. And so it would stop itself when I send it to stick and yeah, keep going. So it's and so I also implemented a very simple guided mode kind of thing, which just sets the target position of the position grid. And so that was just for convenience and settle if I don't want to, have to fly to specific spots, mostly for the source localization, for seeing where the thing is, so I can set up the flight plan. But yeah, this is not really so much for use on the physical blimp, because on that point you just carry it where you want it usually. So yeah, next we applied it to source localization. So if you have like a flammable gas leak or another dangerous gas in a building, you can use source localization to follow the gas to its source. And that's why you don't need to be sending people in or that kind of thing, which you can't fully protect people if, if the building explodes or something. So yeah, we've implemented it by generating fairly realistic plumes using Pomkai, which is a puff-based odor plume model, as I call it, and it's as a Python package. And so that gives you a kind of fairly realistic plume model, so we don't need to deal with real odor sources until we've got the algorithm development ready. And so we also changed the parameters so that the plumes are less spotty, because real plumes kind of have pockets of higher concentration in different places. So we spread it out a bit so you get a smoother plume. And so that was to ease our algorithm development before going to the more realistic plumes and then to a real one. And so this plume could be used on a simulated and on the real blimp, because the plume value is sent from the math proxy modular implemented to the blimp, and it picks it up as if it's a sensor. And so it's bio-inspired based on how moths and other insects track odors. And so the cast and search algorithm casts side to side looking for a concentration, and it casts further out every time until it detects a plume, and then it moves forwards until it loses its plume and kind of goes repeats on that. So this is the left one is in situ and the right one is on the real blimp. And so you can see there's very minimal casting, because it starts casting the moment it loses the plume, and the first thing it does is it casts back toward the plume. And so that's kind of optimizations to get the algorithm working as fast as possible. We also implement a levy walk, and so that's a type of a random walk, and it just moves in a random angle and with a move length given by that formula. You can see that's what the items mean. And so you end up with this kind of path because of the blimp's position control being slightly softer. So you end up with rounded path instead of the spiky paths that you normally get. PSO is particle swarm optimization, which is for doing source localization with multiple blimps. And so this improves the performance a lot if you can wrangle having multiple of them in there. And there's quite a lot of literature on different implementations, but no one has done it on blimps that I know of. So yeah, this was only done in Siddle though, because building 5 blimps, it's painful. And so that's the formula on there, which it essentially sets the target velocity, which it calculates by a weight of the target velocity. And then it takes a personal best, which is the position of the best concentration that the individual blimp has seen, and also a weighting of the global best, so the best that any of them has seen. And then also an avoidance force, which is that FT. And all of them, except for the velocity, is multiplied by a random number. So you get, so they don't end up just going forwards and backwards. So that winds up with that type of path, but it's very different every time. So this is also that conference papers have put out, and so they go into a bit more detail of what we did. And so yeah, future plans is for waypoint navigation, which is kind of the plan is to implement some of Copter's libraries, and so that's going to be depending on the reworks, and that's how we've so we also want to implement propeller based blimp support. So that's the more common configuration for indoor blimps, mainly because it's much easier to set up, because servos are finicky and they die very quickly when you use them like this, which is why it's a problem. And the fins, they need to be in exact offset, so being able to use propellers makes it easier, but they also cause more disturbance, so that's why for source localization the fins is kind of a better application. And then finally the kind of air scale blimp support, which would be more for outdoor blimps. We actually have an elevator and rudder at the back for more cigar shaped blimp. Any questions?
So on slide 16, you had the formula for the search algorithm. And I was just wondering what the subscript G was on the so you had that second line there, so you got Y next to that, there your two coordinates.
So the YK is the personal best of each blimp, and so the YG is the global best.
Oh, okay.
So you're just getting the distance between that blimp's current position and its global and the global best.
Okay.
How long will the blimp maintain enough lift that it's flyable without leaking down and losing gas for this style?
So this one, usually we need to reinflate it about every 2 or 3 days if I'm actually flying it every day. But how soon it would lose enough that you need to adjust the ballast, I'm not too sure of. But I fly them usually, a couple hours in the day, and I don't generally need to do too much adjusting during that.
And what's the battery like?
So on these batteries, I get about 15 minutes, depending on how hard I fly them and that kind of thing. But a large portion of that's because it's such tiny batteries because of the remaining lift, and especially in Bicon with the extra stuff on it for that. So and there's also the flight controller isn't is actually quite a high proportion of the total current draw. Improving that efficiency would really help as well.
Is this the minimum practical size based on all of those, the size and weights, the material size and everything? Is this the minimum practical size you can make this vehicle, or do you think you can train it?
This is probably pretty close to the minimum, but there is still kind of a lot of room for improvement on that, because, for example, I've got an RC receiver which let me use this without having to connect the ground station. But if I did RC overrides, and I could because I've got a Wi-Fi module on there as well for telemetry, then I could remove the RC receiver. The flight control board weighs 7 grams, which is quite a bit for this blimp. So I could go to some of the like 16 by 16 kind of tiny FPV flight control boards, and that would help free up a lot more weight, and then it might be able to fit into an even smaller blimp if one wanted to.
When you like how is the lab position? This one, I couldn't see like little balls on it.
Yes, so it's got reflective markers that you place on the blimp. And then the Vicon cameras pick up the reflection because they've got infrared LEDs, and so they pick up the positions of that markers and like triangulate the position based on that. And then that comes in via the Wi-Fi module. Yeah.
I was just wondering if that search algorithm should be used for thermal finding the source. Kind of looks like it might.
Yeah, so if it doesn't change position too quickly, then it probably could be. It could be an interesting application. Yeah. I haven't heard of it. Yeah.
Could you do wireless charging? So I was just thinking about the power seems to be the only limitation for the. You had a practical one that actually was looking for gas leaks in a large building. Then you could actually potentially have wireless charging points where the blimp sort of sidles up to a point and then charges. Does that make sense?
You could do that, although that's depending on how much range you have in where the blimp needs to be.
Mm-hmm.
If you had maybe some form of an electromagnet, so it's like you can actually hold it there while it's charging,
Mm-hmm.
and then release it so it can go. Because otherwise, you can see it doesn't really stay in one spot at all.
Yeah.
Like that's where one of the things in ArduPilot I was kind of not sure what to do with it, because there's no real land detection on blimps. You can't detect the landing. There's not a real definition of it.
I wonder if you could use a laser on a tracker that has some sort of signal that uses the laser energy to generate the charge battery.
Yeah. Could do. So also if I'll set the blimp flying again, and if anyone wants to have a go flying it.
We try and send it out over the audience.
It's kind of got this thing hanging down.
We got actually the air conditioning just here, so.
Yeah, it seems to be off at the moment. So you basically wait for the gyro to start up, I notice.
I think this is a good logo. I'm fairly sure it finished. Like I turned off the gyro count.
Okay, so it's just the boot process.
Yeah.
Don't let peer pressure make do anything. Is that what happens with the surveys that start to go, or is it?
Yeah. This one. Yeah, it needs to be replaced.
For a security device, if you had this tracking a criminal in your building, they'd be so activated that they'd just be mesmerized until the police arrive.
Yeah.
Fantastic. Yeah, you can find another scripted aerobatics. So that was fantastic. Thank you so much, Michelle. All right. So
yeah, it does vary a bit, and also the inflation amount changes, which is makes traveling quite difficult. It means I have to add inflation in the year. Yeah.
So thank you very much, Michelle. And so the next speaker we've got is Randy. And it's going to take us a couple of minutes to juggle because Randy is also our main recording person. So I'm going to shuffle over where Randy is and take over the camera to record. Randy, you don't want to use my laptop, your slides, do you?
No, I can pretty
Great, so use that one, and I will come over there and take over that.
have them. So this is just a game-changing gimbal, I think. I know it's a bit of a cliche to say that, but that's quite new. And it's also other is the ZR10, which you'll see on the Leonard's again. We've got the View Pro, which is I think from the first video. This is the one that I have, the Q30 TIRM, RGB thermal, also has a built-in LiDAR. We've got support for this, again, using a Lua scripting driver. They're quite expensive. And then still work in progress, but there's a Japanese company called Zacti, which makes a number of gimbals, 5 or 6 gimbals, and they use the DroneCAN protocol with custom messages. So I'm working on support for that. Hopefully that'll be done in the next month or so. And there's also a number of other gimbals that are in the pipeline. It's a company called Otis, I think, that we're hoping to add support for. And I'm sure there'll be more after that as well. So although we have support for all these gimbals, the features that are available are a bit gimbal dependent. And the reason is that it really is a 3-pronged approach. So we've got the gimbal manufacturers that are adding new features. You know, we're in quite close contact with a number of these manufacturers, and we're telling them what we need. And you know, at least especially in the case of like Gremsy and C, they're responding relatively quickly with new features that we need. So, you know, they build out the features in the gimbal, then we expand our drivers. Sometimes we need to expand the abilities in ArduPilot. And so yeah, those are 2 of the 3. And the third one is the ground station development, which I'll get to later. Anyway, this is a grid, which shows you the kind of features that we've got for each camera so far. And the plan is to try and get it all green or yellow. So you can see in the case of the DJI RS2, we only have angle and rate control. It doesn't have a camera, so you know, we can't take pictures or video or anything. We can, of course, do the location control. You can point at a particular latitude, longitude, but ArduPilot's doing all the hard work there. For the Gremsy, you can see it's mostly green right down to focus. So we don't have focus control yet, but they're adding that. The second and the last one is picture including location. That's what that means. So what this feature is that, I mean, this will be a really great feature for mapping. It means that we'll be able to embed the lat, long, altitude, and attitude of the vehicle into the image, into the picture, and that'll allow us to stitch them together much more easily later. Image tracking or visual tracking, you'll see we don't have any support for that for any of the cameras yet, but I think that's coming this year. Yeah, so I guess you can look at the rest of them yourself. Apologies if I've got any of them wrong. It's possible there's a mistake here or there. It just meant as a guideline, really. I guess one more thing to point out is that they are using different interfaces. So some of them use Mavlink, some of them have their own custom protocol. Obviously, we hide all of that down in the ArduPilot drivers, so that you know, as a user or ground station developer, you don't need to worry about the differences.
Ready?
Yes.
So is Lua going to be the way forward for most of them?
That is a good question. I think that's definitely up for debate. I think the great thing about Lua is that it allows us, you know, as Trud said in his talk, allows us to add support for a new gimbal between releases. So if we can get all the basics done, all the basic support, you know, available to Lua script, then, you know, even if ArduPilot, say ArduPilot's moved on to 4.6 and this, you know, particular, you know, manufacturer's vehicles are still back at 4.3 or 4.4, they can use that gimbal without having to upgrade everything. So that would be really nice. For example, the View Pro gimbal, I've wrote that in Lua, and I'm having serious second thoughts about whether I'm seriously considering moving that to C++. And the reason is that View Pro has about 80 cameras. And I'm not sure how many of them will, you know, all use the same protocol, but I think Lua is slightly harder to set up. And so if we've got a lot of users of a particular gimbal, I think we should move that driver from Lua to C++ if we can.
So is the reason that you have 80 cameras, you have to have 80 implementation because of slight modification?
We'll have to see. I've only got one camera myself, and it's a fairly high-end View Pro camera. So it has pretty much all the features.
Right.
So I think if I can get all those features working in our driver, then it will support pretty much all of the View Pro cameras.
Right.
But
I mean,
remains to be seen.
It is, the issue is like you have to duplicate, the code, basically for one camera
Yes.
protocol. So if that is the problem, we are actually adding some, maybe or
Yes.
potentially adding support for required in Lua, which will actually allow you to include common functions.
Yeah.
So that could potentially make things like this easier, right?
Yeah, so maybe to paraphrase what you're saying, so I think you're suggesting that we couldn't support 80 different drivers in C++ because the flash cost would be too huge.
Right.
So, but having 80 different Lua drivers would not be a real problem because a user would only load one at a time,
Yeah.
typically.
Yeah, and also what I'm saying is the development issues that you have in Lua is basically inability to share common methods among different drivers.
Right.
So
Yeah.
that potentially will be coming in ArduPilot as well. That should make it easier for writing drivers like this.
Yeah. So yeah, I mean, you can always copy paste, but it becomes unsupportable
Yes.
at some
But
point.
having a common method basically, and then you can use that, Lua would be a good thing. But
Yeah.
potentially will be adding that as well.
Okay. Okay, great.
I think we could also work on improvements to the ground station for installing Lua scripts.
Yeah.
And it could be like a Lua scripts panel, what list of the ones you've got installed.
Yeah.
I want to install this from the main repository, what version is on there. Something like that, which behind the scenes, so the underlying functionality is there with the FTP client, but it's just not presented in a way that's really easy.
Yeah.
And I think we could improve that and make it possible to have a applet control panel in the ground station.
Yeah.
Maybe those applets can have their own version as well.
Version, etc.
Version, stuff like that. So you can, they can have their own sort of version and have things in the background.
Cool. So yeah, lots of good suggestions there for how to make the Lua drivers work better or more easily. Yeah, I think for now with the View Pro one, it's great to have it in Lua as a test case because like I said, if we can implement all the features that this camera provides in Lua, then we can cover, we've got the bases covered. So, but maybe after I'm done that, we might consider moving it to C++ to make rollouts easier or set up easier. Okay. Right. So next one is Mission Planner controls. Before I started this project, I had no idea about all these controls that Mission Planner has. People come and, as I'm working on these drivers, I'm passing the people and saying, can you please help me test? And I'm finding that many people don't know. So I just wrote this little slide here to demonstrate some of the actions and tabs that we've got available in Mission Planner to control gimbals and cameras. So on the bottom left here, this is the Mission Planner data page, and we've got the action tab, and there's a little set mount button at the bottom left. Probably most people know this, but in here you can set the mode basically of the gimbal driver or the AP mount library. So retracted makes it usually go to 000. And then you would switch between RC targeting, which means the pilot's in control of the gimbal, or Maveling targeting, which means that the ground station or the auto mode command list is in control. So basically switch between those two. Then we've got the payload control. So this is again on the data screen, you right mouse button click anywhere on one of these tabs, and then there's a payload control checkbox, check that. And then you can control the pitch, yaw, and roll of the camera. And the reset button just pushes it back to 000. Then, of course, if you want to point the gimbal at a particular lat, long, and altitude, you can click on the map, right mouse button, click on the map, and say point camera here. and it should rotate to that location. And you've also got the ability to trigger the camera. Most people probably know that, but yeah, you can take a picture easily. Next is the auxiliary functions. So as Michael said in his presentation, I'm a big fan of this one, and I actually asked for this one to be added because really, now that we have all these controls available for gimbals and cameras, you just don't have enough switches or knobs on your transmitter. So this auxiliary function page allows you to control control the zoom, the focus, take a picture, start and stop the video. Also turn on lock and follow mode of the camera, or sorry, of the gimbal.
Are they just method commands? Just
Yes.
commanding directly into the auxiliary function?
Yes.
List.
Yes, these are the it's a real-time command, but yeah, it sends the do aux function command. And like I said as well earlier, we have about 150 different auxiliary functions that are available on switches. So you can set up any one of them here, and it'll be just like you had a switch. And by the way, everybody knows the difference between follow and lock on a gimbal? Maybe not? Okay, yeah. So I didn't know about it either before I started this project. So follow means that the yaw is, by default following the vehicle's yaw. So as the vehicle turns, the gimbal turns with it. And as the pilot is, say, for example, using the transmitter to move the yaw around, that is all relative to the vehicle's heading, right? So you make it point 45 degrees out to the left, vehicle turns left, it keeps on pointing 45 degrees left relative to the vehicle. The lock command means that it is in earth frame. So I have it set up on my transmitter, the top button on my gear link, you click that and it goes into lock mode, and then everything is in earth frame. And that can be either rate control or angle control. So maybe you're again pushing the yaw around, so you push a stick or something all the way to the right, and the gimbal starts turning at 30 degrees per second clockwise. If you're in lock mode, that's earth frame. So again, you don't care what the vehicle's doing. It could be flying an auto mission, making corners and all that kind of stuff. You don't have to worry about that. You're controlling the gimbal in earth frame. Is that clear? Now that lock and follow mode, or the lock and follow mode button that you have, that only applies when you're doing RC targeting. So only when the pilot is in control. Right? The same feature is available in auto modes, but it's done slightly differently. It's triggered differently. Is that okay? Any questions here? So on the bottom right here, I've got a picture of the mission planner plan screen. So this is the mission command list. And in the red, these are all the gimbal and camera controls that we've had for years. So, do digicam configure, do digicam control, do mount control, do set cam drig, dist. These are all there. They all still work. You can keep on using them if you want to. But there's a whole bunch of new ones, which I would recommend instead. So image start capture, that's basically just take a picture. In the future, it actually will have some extra features in it, like time-based triggering. So it's kind of funny. We don't have the ability to say, take a picture every 3 seconds. So people right now, when they want to, take a, do mapping, which is not distance-based, but which is time-based, they actually go and do the setting in the camera normally. You shouldn't have to do that, right? You get what I'm saying? All right. So the image start capture right now just takes a single picture, but in the future will allow you to say, I want to take a picture every 3 seconds or 5 seconds. Then you can also set the zoom and the focus. We've got the video start and video stop. Again, the do aux function as well. So you could, if for some reason you wanted to execute any auxiliary switch function, you could do that. And then the big one, which is do gimbal manager pitch yaw. So this is the one which allows you in auto mode to control the gimbal in angle. You can do either angle control or rate control. So, 0.30 degrees from north, 0.30 degrees relative to the front of the vehicle, rotate clockwise at 10 degrees per second, pitch at 10 degrees per second. You can do all those kinds of things with the do gimbal manager pitch yaw command. It's got a slightly hard to understand flags field. 0 means body frame 16 means earth frame, I think. Maybe I have it backwards. But something like that. Is that cool? Yeah. Okay. So, okay, I guess as a bit of an editorial, this is where we are right now with Mission Planner. It's got a lot of features. They're kind of all over the place. So when you actually try to do it, you actually try to use the gimbal, it's a little awkward. So we've got to improve the ground station. And that brings us to some work that David Sustressus has been doing for Q ground control. And here's a little video from him. Sorry. A little funny, I don't know why it doesn't play. There we go. I don't hear any sound. Do you hear any sound?
How about that? No sound? I think I might need to. Just a second here.
Get your sound sources, your local speakers.
Yeah. Maybe this.
Just set it to your HDMI audio.
Should be, isn't that this? NVIDIA high definition.
That's it.
Nope.
Might have to do without sound in the video.
Okay. All right. All right. Well, I will. That's a bit unfortunate, but I'll try to do the voiceover.
No.
Okay. Right. So yeah, he's testing on the Erase quadcopter. It's got the same camera that I've got here, the CA8.
Right.
And obviously you can see the live video on the left. And right up here on QGC, there are a number of buttons that you can use to control. This work is still work in progress, by the way. It's not merged yet to master, but it's getting there. So yeah, this is where you can select whether it's yaw lock or yaw follow, that feature I was just talking about a second ago. This is maybe the coolest feature. You can just click on the screen and it will move to that heading or that angle. That's both, that's in 2 dimensions as well. It can do this because it knows the field of view of the camera. That's a setting that the user has to set.
Is that only a camera control? Is that changing the navigation of the vehicle?
This is not changing the navigation of the vehicle. This is just for the gimbal. So yeah, you click on the screen and the gimbal will point to where you're clicking on the screen.
Does that use the terrain map for the vertical angle?
It doesn't need to because it already knows the attitude of the gimbal. And it knows the field of view, so it's just got to be like 10 degrees up and 15 degrees right.
I'll tell you what, there is to be a very small step to actually add in a guided go-to gear mode.
Yeah, I've got a slide on cool feature stuff. It doesn't yet do the rate control, but that is also going to be coming. So you'll maybe click on the screen and then sweep left or right or up or down, and it'll then rotate at a certain speed.
Is that a function of the camera or some code has been written in the QGC?
It's really mostly in QGC. So we've got these new controls that like that Do Gimbal Manager pitch yaw, which exposes all these controls suddenly. And then the ground station can take advantage of it to do cool stuff like this.
That's independent of gimbal and anything.
It could be any gimbal. It could be a servo gimbal.
Yeah,
Yes, you can see him again pointing
here
here and there. Yeah, he's also, yeah, you can also easily change between RC targeting and MAVLink targeting. So back on, Mission Planner, you have to change tabs and to change the mode. He's got an easier to find mode selection button. He's also got the ability to, put it back in center or face 90 degrees straight down. And in this next section, here's the point straight down, I think. Yeah, there it goes. That's easy to find button to make it point straight down or point at home. And this is how you can do ROI. So it's got a little ROI selector, then you click on the map and it'll point at that lat long altitude. You can also manually type in the lat long altitude. And the next part of this video is just demonstration that the same kinds of features work in auto mode, again using the Do Gimbal Manager pitch yaw.
No, we should address that.
Oh, maybe it's here. I was unmuted here. I'm sorry. Yeah. Yeah, when I was trying to get the video sound working, I unmuted myself. Okay. All right, back to the. I get out of this screen. Oh shoot! Wait. Okay. So another kind of cool thing that we've done recently is the Mount POI Lua script. This is just a simple example of, of just one basic feature that somebody asked me for that we can now do now that we've got all these extra controls. So basically, the point of Mount POI is that it tells you the lat long altitude of what the camera is pointing at, and so the reason it can do that is because ArduPilot, of course, knows the position of the vehicle, it knows the gimbal angle, and it knows the terrain, not just the terrain underneath the vehicle, but the terrain out to as far as you want. So the way that it works is it checks it basically moves out in a line from where the gimbal is and from where it's pointing, and it checks every 30 meters or so to see if it's above or below the terrain. So the moment that point falls below the terrain, then it linearly interpolates between that point and the previous point, and it says, okay, that must be the lat long altitude. So, and then it draws a little camera icon on the map. So this is some testing that I did in CITL, and it worked. And also, Philip and I tested it the other day at CMAC, and we actually pointed it at a mountain, and the little lat long altitude of the point on the mountain appeared. It wasn't super accurate, but I'm sure it'll get better in the future. If you want to have a look at the script, there's a link to it here. It's in the examples directory for the moment.
Was the lack of accuracy only altitude, or was it lat long as well?
Definitely lat long as well, especially if the vehicle is low. So the very first test that we did at CMAC, it was only about 50 meters away and about 15 meters up. So it's quite a gentle slope. And so that means that if there's any kind of like altitude error or any angle error, it turns into quite a large latitude longitude error. So it was. We'll have to see how accurate it is.
It's a limitation of your measurement accuracy from the gimbal.
Exactly. I actually suspect that a lot of it comes from the gimbal, but I'm just throwing shade there at that point. We don't really know. That's just a guess. Any questions? Okay, so some of the immediate next steps that we're going to be doing. Zoom position. So right now you can control the zoom of the camera, but you can only say zoom in or zoom out. We really need to be able to control the zoom in an absolute sense. So zoom to 30 times, zoom to 6 times. We don't have that yet, but it's coming. Same thing for focus. We can focus in, focus out, but we can't say focus to this many meters or this percentage. We want to send, and just to explain why that might be important, those two things. Just at the bottom, I've got a couple of little cartoons. One thing I wanted to do was a dolly shot. I don't know if you know what a dolly shot is, but it's that slightly strange effect they sometimes have in movies where the person seems to stay put, but the background zooms in or zooms out. I thought it'd be really cool to do that with a drone, and I think it would be possible if we have better zoom control, if we have absolute zoom control. For the focus, you can imagine, I mean, how many times have we tried to film a drone flying in the sky and the camera focuses on the cloud behind the drone and it's all fuzzy. So if we have proper zoom control, then, you know, maybe our antenna tracker, you know, or maybe a gimbal mounted on a rover or something like that could take a really nice clear video of our flying vehicles. We should also send the camera information and camera FOV status Mavlink message to the ground station. So in that video from David, he could click on the screen, right? And the gimbal would point there. That only works when the camera is fully zoomed out. If you zoom in, it's going to sweep far too far. And that's because it doesn't have an update of what the field of view is right now. So that's why we need to add those messages. Also send video stream information. Right now, the setup in, say, for example, Mission Planner to get a real-time stream of video is clunky, right? You have to go in there yourself and type in the IP address and other things. Some cameras, like the View Pro, tell us what their IP address is for the video stream. So we can send that to the ground stations and they can just get it automatically. They can get it immediately with no user input required. Also, the camera track point and camera track rectangle message support will be added for the View Pro. So this is where a user could, for example, click on a person in the video and the camera will track that person, or they could select a little square around a house, something like that. And the camera will track that, that object from then on. So we need that support for that. Those are the immediate next steps. There's a lot of other things after that. So this next slide is really just to try and get people thinking. For example, in Robert's Mahoney's speech earlier, he talked about how he treats the camera as a sensor. And I think with these new controls, these new abilities, we can do the same thing. It's all kinds of new cool stuff that we can do. So one of them is visual tracking and follow me. So of course the View Pro can, you know, internally the gimbal itself can already track a person or house, what have you. But, you know, there's no reason why we couldn't do the same thing with these cheaper cameras as well. If we had maybe a companion computer, which could take that video input stream, do some OpenCV, or, you know, maybe TensorFlow AI image processing, and we could achieve the same thing with a cheaper camera. But then, as Leonard was talking about earlier, mentioning maybe we could follow the person, right? We could maybe estimate. We know what angle the person's at, so it's easy to point the gimbal. But now maybe we could say, well, we know that that's Reshap. He's 1.8 meters tall or something like that. And so therefore he, you know, with this field of view, he should be this many pixels high, but he's not, he's smaller. That means we're too far away. We can move towards it.
We can do automatic inspection on a tower or a building.
Yeah. Also, some of you may have heard of the Open Lander project. So this is a project which uses the Luxonis AI cameras to perform safe landings. You know, maybe we could do something similar with a regular camera. Again, piping the image through a companion computer. How about high altitude optical flow? You know, I think our optical flow sensors right now have a very wide field of view, and they're designed for low level flight below, you know, 30 or 40 meters. That's kind of their limit. But what if we have a camera like this with very high, you know, with 4K, 6 times zoom, the other one has 30 times zoom, good stability? Maybe we could do optical flow from a much higher altitude. Maybe object avoidance. anyway, there's a lot of ideas. I welcome everyone's ideas. One thing we'll definitely need though is a development environment, so that we can test out these algorithms before actually putting them on vehicles. Okay. Any questions on that? Or comments?
So just one comment, I mean, the moment you get into processing vision, right, you really get into the hardware testing as well, and you talk to the environment, you talk to the environment, what's really trying, if you want to do TensorFlow, you really need to start thinking into the GPU, the AI stuff. So we ran into this actually with Shell a while ago, and we were trying to get, trying to do VIO for ArduPilot, and it was just, what's the compute environment?
Yeah.
And trying to figure out how that fits into an open source code environment stuff is too hard for us at the time.
Yeah.
It's a hard one.
Yeah, for sure. Philip, do you have an answer?
On that one, there's going to be variables and things with video send them on it. That's what they see. Well, it's blue. People give it the execute that and bringing it into that and sure. Yeah.
Okay.
No, full advantage. There's full courses.
Yeah, for those people who were listening in and maybe couldn't hear the questions or the comments, it was really around the limitations of, or the CPU limitations that we've got on our drones, and what do we do about that? And so I guess the answer was we have numerous carrier boards that do allow, powerful companion computers. There's also the HereLink receiver was brought up, I guess, as a possible GPU that could be used, or CPU that could be used. Yeah, I'm sure. So. Yeah, obviously the CPUs that we've got on our flight controllers, the real-time CPUs that we've got here are not capable of doing image processing. I think that was clarified when we had the Cube Red presentation. All right, another open question is how much communication do we want to allow / support between the ground station and the gimbal? So one thing that I noticed at the beginning of this project was that a lot of manufacturers were writing new plugins for the ground stations to give the pilots better control of the gimbal. Sometimes they use the Mavlink protocol, sometimes they use the custom protocol that the gimbal supports. But in any case, they were completely bypassing the autopilot, and it's just straight ground station to gimbal. And I mean, that's fine, but it does cause a number of problems. One of them is that it means that ArduPilot can't do all that cool stuff that we were just talking about. It has no idea that the gimbal is there or what it's doing. So there's a whole bunch of things that we can't do that we might like to do. Also, it means that we end up with a whole bunch of different solutions. Like we'll have one for the CE camera, we'll have one for the View Pro. They're all different. That's not a great user experience. So from my point of view, at least, I'd like to have as little direct ground station to gimbal communication as possible. I think ArduPilot can do a good job of hiding the differences in the gimbals, but inevitably, I think there are going to be some really special features of some cameras that ArduPilot will never support, or it'll take us a long time to add support for. And so I suspect that there are some situations we're going to need to allow that communication, and I'm not sure how we're going to do that. Especially, yeah. So open question. We can discuss it now or on a dev call someday. Matt? Yep.
I think we're ArduPilot and we should remain that. I certainly see where you're coming from in trying to provide an interface that would sort of smooth that out. But the reality is, I think a lot of the gimbal manufacturers are all going to be doing their own thing. And I just don't think it's really going to be that achievable to kind of smooth that interface out perfectly. I totally agree that support generally, but I think that the UI problem is more than a ArduPilot problem.
So you don't think we should? You just think we should definitely allow all that kind of communication, but you do agree that we should at least do our best, right, to support as many features, as many basic features as we can, right, in ArduPilot?
Yeah, it's just, like, a lot of people seem to be achieving a lot of this already. A lot of our customers have certainly done this kind of stuff. I'm certainly like not an expert on how they integrate that kind of thing. But it seems to be already being done, so it's just a case of, it feels more like a UI problem, that's all.
Yeah.
The problem with treating it as just a UI problem is then it can't be automated by the vehicle in a VV loss situation. It relies, so I want the vehicle to be able to choose its zooms, choose its focus point, etc., based on data being collected by the vehicle when it's over a very thin tether. So I'm setting it out on a task, which is a vision-oriented task, which it needs to be able to achieve itself. Now, at the moment, I've got one of the cameras that all of the implementation of its controls are in Mission Planner. And Mission Planner can't be running on the vehicle doing those controls. And I'm on a very low bandwidth link back. And I want it to go and gather that data and be controlled from within the vehicle. So if it's only implemented inside plugins in Mission Planner, it completely precludes the types of automation that ArduPilot is good at.
And also multiple vehicles, like what if you have like multiple cameras that is and what plant that together and make them do, you know.
We want it at least acceptable in Lua scripts, and for that, we have to make it that the vehicle and the flight controller understands and is able to control what's going on.
Is that quite true though? Because a lot of the examples you just gave could equally or arguably better be achieved by an onboard computer.
Only if it's got the implementation, those that tend to be proprietary plugins to the ground station, right? So we've got to have implementations of those which are pliable.
Yeah, completely agree with that. I kind of agree with Matt though, that I think that if we try to do all of this in the ArduPilot for everybody, that gets unmanageable.
Yeah.
Well, we could make the distinction of on the aircraft versus on the ground there. I think you're sort of saying that. The example would obviously be the good old solar. The implementation of that gimbal gave ArduPilot a lot of control over how that gimbal worked, that it's been working together, but it still uses mechanical computers to do some full scripting and stuff like that. But yes, it was all done on the aircraft itself, so it wasn't reliant on the
A lot of what I've seen is like a companion user with significant compute power is doing some image processing. And we already provide the hooks from that to request the autopilot to tell the vehicle where to go. So instead of the autopilot telling the camera and stuff, there's another layer on top, which is, you know, we're like focusing on finding the vehicle. And then the companion computer is saying where it wants to go and controlling the gimbal and that kind of thing.
Yeah.
So that was just kind of where I was coming from.
Yeah.
So philosophically, it's saying that if you have the companion computer, you can put a lot of high-level functionality there. You can do machine learning stuff and all sorts of things to work out where the vehicle should fly, where the camera should point, all those sort of things.
Yeah, but there is also that remake mission level stuff that you do, but that's primarily handled at the autopilot. So in that particular scenario, you would probably want to make like camera pointing and all that part of that mission key, which means that control lies on.
Yeah, this is kind of what we talk about basic functionality, where it's all it's scripted and you're not going to deviate from the plant mission plan, through to something where you want the vehicle to operate over a skinny link along together and operate autonomously.
So maybe I should be both then.
I think if we can do both, that would be best. But how do we? We'll then have to provide some kind of tunneling mechanism or something, you know, to allow, for example, a ground station to speak in perhaps the gimbal's native protocol, but over Mavlink. I don't know. Or maybe we have Ethernet. Maybe we can create different channels using Ethernet. I don't know.
Really, Mavlink gimbal V2 service abstracts that concept as a gimbal manager away. So that gimbal manager can do a pilot and the ground station doesn't actually know where you put that as far as that is.
Yeah, that of course assumes that the gimbal has Mavlink gimbal controls implemented. Some of them do, some of them don't.
The camera itself doesn't consist of the gimbal manager, so we're talking what part of the ground station for that manager.
I think you're saying if you have like the autopilot can send that link connects to something managing the gimbal, that could be like the onboard computer that then actually does has the driver support.
So was there?
Continuation, I say that in a piece of history that nothing implemented, none of the cameras that we were implemented that or any standard that anyone would have targeted originally. So it was a lot easier to, in the first instance, to have a companion computer and show a camera manager that would do what the blue roll stuff does. So if you were starting out, you would have the same question you could have with your scripts or companions to do these kinds of things. What would you do now? Can you rely on the interface? Would you plug it in to your product? What benefit would that give you? So that's
Yeah. Well, I mean, I think there's definitely tons of benefits for having the autopilot in the loop. I mean, Trish just mentioned a couple of them, you know, giving us autonomous control of the camera. But there's also just cases where, you know, ArduPilot has a lot more information, like the mount POI is just one simple example. You know, most companion, I mean, I guess companion computers could get the train database from ArduPilot if they wanted to. But ArduPilot's got it right there. I don't, for me, it just definitely seems like ArduPilot should be in the loop, you know, should be implementing the gimbal manager. But okay, I think that's all right. Is there any other questions or comments on that last one? No. All right, so just if you want to get involved, here are some suggestions. There are a lot of gimbals out there, and my office is filling up with them quickly. But I would love it if others could help me test them. And I've actually had, you know, good response in the forums from various users who want to help me test. But you know, more beta testers is always welcome. You could get involved with the enhancements. QGC is looking pretty good, but you know, Mission Planner, you know, could be improved. So if somebody wants to help out there, that'd be great. Like I said, there's a couple more gimbal drivers that are planned that I have not even started on yet. You know, if somebody wants to write a camera gimbal driver, I've got a couple of suggestions. If you are a manufacturer of a camera gimbal and you want to have ArduPilot support and it isn't on that first hardware page that I showed, you could send me one, or you could send one to one of the other devs. So far, the manufacturers have been very good about providing hardware. And then there's a whole bunch of Mavlink related, Mavlink message related issues that we should solve. So if you look at these two issues, you'll see a big list of line items that we need to work on. And the last one is just that AI integration dev environment issue that I talked about earlier, piping the video into a companion computer, you know, getting that all working under CITL. We've got an issue for that as well. So that is it. I just want to finally thank my main sponsor, Eames, who's been supporting me for many years and allows me to work on all this fun stuff. Thank you very much.
So thank you very much, Randy, and apologies for those online. There was an audio problem in the first few minutes of Randy's talk. Apologies for that. Alternative is to go out to the flying field and have it on the screen inside. You've got a large TV presentation screen. Now, when I discussed with John earlier, we're imagining having it on the screen All right, so we want a few minutes on now. So John, did you want to come up for a few minutes? You all ready to go? We are a little bit ahead of time because we were going to finish up at 4. And so we've got a few minutes we can go now. And all right. You recording here? Yeah. Sorry. Okay, so this is the bonus talk we've got from John Challenger on state estimation, the future of state estimation in ArduPilot. Now, are you sharing your screen, John?
Yep.
That's great.
There we go. Okay, I just wanted to talk a bit about where I see the future of state estimation in ArduPilot. And this is meant to be just some concepts and ideas for that, as well as an introduction to the very high level math spree explanation of how state estimation works. Concepts and ideas means that this is this is definitely up for debate, and I'm not trying to say this is the way, but I'm trying to start a discussion. All right, so currently we use the extended common filter for our state estimation needs. An extended common filter represents its knowledge of the world as a Gaussian. So basically, these fuzzy blobs here, you can think of them as an ellipse or an ellipsoid, and it basically has 2 steps. It predicts the next. Yep.
John, sorry, I really may not be just thinking about what they may or may not know. I don't know what Gaussian is, but I can just say that it represents, you're having a guess at what time it is, and that blob represents the uncertainty.
Yes, and yeah, actually, Paul, why don't you just come up here? Yes. So essentially, it represents a probability distribution or a region of uncertainty. Yes. So again, the filter is implemented in 2 steps. So the first step is the prediction step, where the filter models the change in state and the growth of its uncertainty in its state over time, using its knowledge of the system dynamics. So if you know where a car is and how fast it's going, you can predict where it is. You can predict where it will be after a short period of time, but your uncertainty as to its location grows. The imperfections in the dynamic model are modeled, and that's and called process noise, and that kind of determines how that uncertainty grows over time with each prediction. And then there's a second step, which is the update step, which is where we shrink our uncertainty back down. We collect real world observations and update our understanding of the world based on those. And those observations themselves have a probability distribution. So essentially, if our state is the black circle, and we observe our observation is the blue ellipsoid, then the result of the fusion of those would be the green ellipsoid. And this is a bit of a simplification as the filter states don't have to be observed directly. So we, in order to estimate our position, we don't need a position observation. We can use something like a distance to a known point or something like that. And the filter will fuse that knowledge in. So the disadvantages, and I found this little animation, which is pretty good. I just included that. So you can just kind of watch that while I discuss the disadvantages. The disadvantage of the extended common filter are that it can only represent state and observations as a Gaussian distribution. So if you wanted to say, have a uniform distribution of state over an interval. So for example, a uniform distribution of heading over 360 degrees. You can't do that with an extended common filter. And then it also can only have kind of one hypothesis. It's kind of an extension of that. You can't have an extended common filter that thinks like, I could have this state or this state, right?
Only get one guess.
Yeah, you only get one guess. And then due to the way that the extended common filter linearizes things, it only works well when the estimated state is close to the true state. So convergence of an extended common filter is not guaranteed. Yeah, that's the issue that prevents us from estimating our heading without a compass. Essentially, is it can't converge from that far away, right? So the solution that I would propose is called the Gaussian sum filter. We're currently using it, a little mini version of it, for heading estimation. Essentially, a Gaussian sum filter represents its uncertain knowledge of the world as a weighted sum of Gaussians. So we've got these little bell curves here, right? And the blue line here is the sum of them, and so that would be the this filter kind of has two main hypotheses, or this distribution kind of has two main hypotheses as to where the truth actually lies. And that's what a Gaussian mixture filter would allow us to do. The individual elements, I call them mixands because that's kind of the nomenclature in literature. And the advantages are we can represent a non-Gaussian probability distribution of state. So for example, a uniform distribution of heading from 0 to 360 degrees. And we can represent multiple hypotheses. And it addresses convergence issues caused by the EKF due to linearization, which you can kind of see in this comparison here. So a Gaussian sum filter sees the world like this instead of like that. It's a little more detailed. All right, so the Gaussian sum filter is literally just a bunch of EKFs. And each EKF represents one mixand, and the filter can have multiple hypotheses and can approximate non-Gaussian probability distribution. As I'm repeating myself now. So you know, this is a kind of a diagram that I did to talk about how a Gaussian mixture filter is updated. So it kind of it's just you have these two EKFs and you do their prediction, and then you do their update with some observation. All right, so we have this this row here would be the state after the prediction, and then we have some observation. We fuse that in, and then the magic step is the reweighting. So we apply a weight to each of these filters. So each EKF has a weight, and the measurements that are more consistent with the state, or so rather the filters that are more consistent with the measurements get weighted higher. So each time you use the measurement, you're also reweighting all of your filters.
At the moment, we can quite easily run multiple EKFs.
Yes.
Have that much to install.
Yes, and we're not using nearly all of the processing power that we have.
I've got 65 grams of extra flash thanks to the campaigns.
Bringing those existing camel filters together as a gas and sun rather than just running
we're not running a median across them. We do something similar to this, where we have some kind of handwritten logic that decides when we should do a lane switch. And rather than doing that, we could use these techniques to do that instead. And I think that is a good idea that would simplify things potentially.
I think there's a distinction here between, like, there's other median filters where you have three ecos that are initially all running their own best guess. You haven't started off with, you know, so you've got IMU data coming in, 3 different sets of IMU data, guess are running, and they're all pretty close to the truth.
Yes.
Right. And the median sector is the great algorithm for that.
Yeah.
Because this application is where you start out, don't have a clue what it is.
Right. Well, this could be, I think what you're talking about is the application of this to the lane switch, essentially. And I think it is applicable to that. And it provides a statistically robust and simple framework to accomplish that kind of thing.
And I just want, and I just want to make a point. I can't see James. Sorry. You're hiding around there. Essentially, we take our multiple EKS at the moment, and then when we end up with a large amount of one EK gets pretty unhappy and starts projecting measurements, we go and we find the one that's most consistent with its measurements, as in the highest weight. But rather than just get the weighted average, it's okay, now you'll find the one. Yeah, that's right. Yeah.
And I guess what I was saying is, well, this is quite a complex work. What I was suggesting is that at the moment, we're just doing a very coarse line switch.
Yeah.
The transition to whatever. You could just be using all of them.
Yes.
Yes.
That's right.
And it would it would require extending the state vector of the EKF so that it has bias states for every IMU. So it would add 6 or 9 states per additional IMU.
We currently, for the IMU switching, I added in some code some time ago that estimates bias states on the other IMUs in case we need to switch them in the future. So
Yes, that is implemented as a separate filter, but it would definitely be a little more robust, I think, to have it just extend the state vector of the actual EKF. And of course, everything is a trade-off for when you do that, you yeah, computation and memory and so on.
And also, is it worth looking at maybe distributing it among different like nodes as well, like what you have like a
Possibly. I'd be concerned about the IO overhead of that. So let me just continue on, finish the introduction and get into the applications afterwards, because there's yeah. Okay, so then there's another level to this. So Gaussian mixture filters can also use Gaussian mixture observations. So you can have an observation that says, you know, I might be seeing this or I might be seeing this. And the filter will use both of them. And when this happens, the number of mixins grows, is multiplied by the number of mixins in the observation. So essentially, you end up with growing the number of mixins exponentially in time, and then keeping that under control by kind of fitting a new, simpler mixture that matches as close as possible the detailed state of the filter before reduction. So we can see that working here. So we have kind of two of those predictions happening, and then we have 2 observations, or one observation that has 2 mixins, and then we fuse those, and we have the result. We have the result of all of those fusions right there, and then we do the reweighting. So again, the most consistent one, like these ones turn out to be pretty inconsistent, and this one was consistent, so we give it more weight and these ones less weight. And then we do the reduction, and we take all of these insignificant ones and we kind of combine them into one. Then we're back to having 2 mixins in the filter. So now I want to talk about the application to INS alignment. So this is an example of an inertial navigation system. It's a full state inertial navigation with, I believe it has 18 states. So it's estimating the attitude, biases, position, velocity. An indoor navigation project. These are little radio beacons. Decawave stuff. So we have another one of these. Right, so this one shows essentially it starts out, I wave it around a bit and then I let it sit on the table for a few minutes. And so as it's sitting on the table for a few minutes, its uncertainty grows. And then it starts splitting out new mixants as its uncertainty grows. So kind of you can let it sit there and lose its knowledge of heading over time. And it will regain it as soon as you move it. And right here, all I did was I just touched it. Kind of figured that out. Right. Oh, and I wanted to, let's see, I have another one here. I just wanted to, I've removed the reduction step on this one, so it doesn't actually reduce them, it just keeps running them. And you can see here there's 8 mixants, so they're separated by 45 degrees. And within 1 second of me starting to move the receiver, 6 of them have reasonably well converged. You know, this is a formula, a parameterization of the states that is different from what is in EKF3. It has yeah, except I've fixed some of the issues with that. So so this could be applied to like an EKF4, or if we want to call it that, a new parameterization of EKF.
When you say
that does.
You mean this is a full 3-dimensional process model, so it's not limited to that playing out.
No, yeah, so this is a full 18-state inertial navigation filter. More states could be added as needed for things like magnetometers, wind, stuff like that, as needed. But it converges beautifully from very large initial misalignments, which means we could potentially run, you know, 4 of these, and not need to have a separate heading estimation filter, right? So instead of using a reduced state vector for the heading estimation part of it and then resetting our main filter, we just have a Gaussian mixture filter for our main filter. That's you know, that's something I would think, especially as hardware gets better. Yeah. I mean, it reduces the complexity of handwritten logic in the code, which always makes things more reliable, as long as, you know, it does what it says on the tin anyway. And it provides a very nice framework for solving these kinds of problems too. Okay, so I wanted to switch lanes a bit and talk about different levels of GNSS integration that are possible. So our current system, we have we typically use new blocks GPS for all kinds of GPSs, but essentially the receiver runs some kind of motion filter inside of it, which is basically its own EKF, except that it doesn't have access to our inertial data or any of our other sensors that would be yes. Oh, okay. All right. I will stay over here then, and I can point with this. Okay, so the current system uses basically gets filtered position and velocity out of our GNSS receiver, which is kind of a black box to us, and we and the disadvantages of that are that basically that filter can't use motion data from our IMU or other sensors to assist in determining which GNSS signals that it should trust. In addition to that, it adds a variable delay to the position and velocity, and errors on that position and velocity that we're consuming from the GPS are correlated through time, which is violating a core assumption of the KF algorithm. And then internally, the receiver knows has a more, I'm speculating, but internally the receiver has a more detailed view of its uncertainty on those positions and velocity, but it only provides us with some very coarse metrics. So we get that speed accuracy or h-stop, etc. Yes.
I have seen a box API that support both variants.
Oh, that would be nice. Yes. Yeah, that would be very useful. Great. That would help a little bit. And then another one that's not listed on here is that their motion filter, because it doesn't have inertial data, it has to make assumptions on the dynamics, which means it would break down under very high dynamics. We use the mode that their highest dynamic mode is 4Gs. So, you know, at some point above that, it's going to break down. Anyway. And when you do maneuvers like that, it changes the delay that it adds to that measurement. The solution that would be great to get to is tightly coupled. Oops, I'm running away from the microphone again. The solution that would be great to get to is tightly coupled. And I only have this ultra tightly coupled on here as a kind of, it's kind of the ultimate, if we can get there, it would be great, but I'm not holding my breath. So tightly coupled is where essentially we do all the GNSS data processing aboard the ArduPilot, and we don't have any intermediate motion filter in there. So
just caveat there, when you say processing, you're talking about the motion filter processing or converting.
Yes. Well, I'm also talking about
converting the delta times.
Well, we've also got to.
You're not going to be doing chip codes and things like that.
No, but we do also have to decode the ephemeris. We have to apply all the corrections. GNSS signal. And that actually lets you turn the gain down on that PLL and make it less sensitive to noise. So it actually increases the received sensitivity of the GPS. And again, reduces susceptibility to multipath jamming and spoofing, since you're less likely to switch to a reflected signal or whatnot. And it could also kind of let it dead reckon its way through a brief noise event a little bit better. So I wanted to talk about this potential application to multipathing. So if you had a Gaussian mixture filter, you could have multiple hypotheses in a tightly coupled GNSS and GNSS INS filter. You could have multiple hypotheses as to the position of the receiver. And so you could do some kind of RAIM-like combinations of 4 satellites, and then use that to find the clusters in that and create a Gaussian mixture distribution of your position. That is ideally as simple as possible. You wouldn't want to have all the permutations there, because that would be insane. And then kind of as you can see here, you know, my explanation of this, I'm running away again. You can see here that the filter is predicting that it has moved. Maybe it got IMU data that says I've moved from here to here. All right, so it updates its mixance, and then it fuses this new observation where one of those solutions got more right and one of them got more wrong. So then it's able to it's basically fusing a Gaussian mixture observation at each time it gets a GNSS signal, and that lets it figure out which groups of satellites or which group of satellites gives it the optimal solution at any given time. So that's kind of this is a bit of a moonshot. So that would be potentially a lot of processing power, since you'd need a fair few filters to represent the probability distribution of the state in this case. So then just other applications that it could be used for are, we already talked about sensor redundancy. So mixins could run on different combinations of sensors, and if a sensor is failing, mixins that utilize that sensor would be deweighted. That could be inertial sensors, it could be any other type of sensor too. And it provides a statistically robust framework for dealing with sensor redundancy with arbitrary sensors. As an aside, it would be pretty cool to add the ability for Lua scripts to add observation models to the EKF. So we could just do we could provide, if we could provide a function in Lua, then we could do the Jacobian of that function numerically. And we could actually potentially make it easier to add observations, add sensors. 5 minutes, okay. And then actuator failure detection is another possible application of this. So an inertial navigation filter that has a dynamic model of the vehicle. So it actually, given some actuator commands, it can predict where the vehicle is going to go. It could have hypotheses that things have failed. So like there's a mixand for that has a dynamic model based on a motor 2 failure. And if that one starts getting weighted, it gives you a probability that that is the truth, essentially. And then you could change the control system, the gains, or the whole scheme to account for that. And then other types of Boolean state detection, like on the ground or touching a wall or something like that. If you had a dynamic model, different dynamic model for when you're on the ground or for when you're touching a wall, or something like that, you could also weight between that and the flying case. So that would also, it also provides a statistically robust framework for figuring out those types of things, for ground detection and so on. Which again, we currently do with handwritten logic, and it works, but maybe and I don't think we have any problems with it currently, so it might be a solution looking for a problem. And then battery state estimation, which I'm also working on. So we get to represent multiple possible chemistries with a Gaussian mixture filter, and that would kind of allow us to give a user a worst case energy remaining, so that they could essentially get a time remaining or a range remaining for their vehicle, that we could implement a fail-safe based on that. Currently the only really useful fail-safe we have for batteries is probably the voltage fail-safe. And then there's just the challenges are for tightly coupled. The challenges in implementing that are mostly related to the complexity and processing and correcting the raw measurements. Actually adding the observation model to an EKF is not all that difficult. Ultra tightly coupled would require a pliable hardware manufacturer to give us the right hooks into their system, which I doubt would happen. Gaussian mixture filters in general, especially applied to an inertial navigation system and compounding all of these different applications, takes a lot of processing power and memory. So yes, yeah, so these things compound on each other as a hypothetical system using a Gaussian sum filter with 5 mixends for yaw, 5 mixends for multipath, and 8 mixends for sensor redundancy is running 200 full state inertial navigation EKFs. So, you know, we're gonna need a bigger boat.
For this, or you can still have some smaller number of.
Yes, yeah, we can do like one of these applications, but we can't do all of them at once.
Yes. Or some sort of distribution model on the aircraft.
Yes, distributed computing would be a potential solution for that, or offboard computing or something. And then also, some kind of FPGA or GPU acceleration would be really nice. So I'd love to hear ideas for approaches to that, and kind of what hardware exists out there on the market that is, somewhere between an STM32 and one of these large, heavy, power-hungry NVIDIA solutions. And they are in relative terms anyway to an STM32. All right, time's up. Some references. That's it. And I'd like to thank Paul and Tridge for being mentors, and Randy for helping me proofread this presentation.
Thank you very much, John. Fantastic. It's great to get a photo presentation at the end there. So now we're at flying vehicles. Now Peter, are you still here?
Yeah, yes.
You can possibly open the gate out there and can see the smoking with opening the clubhouse. I'll be back up here. So I've got room for 4 people in my car. Randy has his van. There will be drinks and nibbles, and then it's going to be the peak of the van arriving. So if you're not at the CLAP at 6:30, you're going to be hungry. And look forward to seeing you all out at CLAP. It was a really fun time, and for discussion of today's and yesterday's talks. Thanks everyone. See you soon.